We are on chapter 10, section 4, which is our cycloalkanes. Cycloalkanes, all you have to remember is that cyclo is a ring. So cycloalkanes, if I took something that was, let's say, 4 carbons long, right? Each of those carbons is going to have a particular number of hydrogens, right? Each one on the end is going to have 3. Each one in the middle is going to have 2. But what if I made it a ring, which would mean that I would have to basically bend the carbons so that I now have, here's my 4 carbons. I'm just going to put them in a ring now. So this is still carbon number 1, 2, 3, 4. This is still 1, 2, 3, 4. And 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. These 2 molecules are exactly the same thing. They're both butane, right? Both of them. And each one would have, the end carbons would have 3 hydrogens, the middle carbons would have 2. But what if I took away 2 hydrogens from each of the end carbons? So from carbon number 1 and carbon number 4, I would take away one of those hydrogens and I would introduce a bond between carbon number 1 and carbon number 4. That would mean I would have 2 less hydrogens than the corresponding straight chain alkane. So now instead of having butane, I have cyclobutane, right? So if I look at the formula of butane, butane is a straight chain alkane. So that should be the formula CnH2n plus 2. So I have 4 carbons. So then I should have 4 times 2, which is 8, plus 2. I should have 10. And that's true. I have 3 on each end, 3, 6. And then the middles is 7, 8, 9, 10. So that's true. Cyclobutane is a little bit different. You're going to have a different formula. This is going to be CnH2n because I've lost these 2 extra hydrogens that were on the ends. So now cyclobutane's formula is C4. It's still the same number of carbons, but now it's just 2 times 4 is 8 because each of the carbons only has 2 hydrogens attached to it. So it's very, very similar. When we're naming cycloalkanes, make sure you put that prefix on the parent so we know that it's a cyclo. And then put your substituents in alphabetical order, just like we've done before. And then if you have multiple substituents, use the lowest number, just like we've done before. But the only thing that's kind of extra is that if you only have 1 substituent on a ring, it doesn't require a number because it's always 1. It's always on carbon number 1. And I'll show you why. So here's some examples of different cycloalkanes. And we have both the Lewis structure and the line diagram so that you can kind of see them. So let's just say I put a substituent on cyclobutane. Let's just say I put a methyl group. So if I stuck that methyl group on cyclobutane, where am I going to start my numbering? Well, I have to number my parent chain so that my substituent gets the lowest number possible. So this carbon has to be carbon number 1. Now, it doesn't matter if you go clockwise or counterclockwise. I could go 3, 4, or I could go 1, 2, 3, 4. It doesn't matter. You would get the same name, same molecule, doesn't matter. Okay, so let's try, don't look at the answers. Don't look at the answers. Just pause the video right here and try to name these. Okay, so the first thing is you find your parent chain. So our parent chain in this case is in the ring, and we're going to number our parent chain to give the substituent the lowest number possible. So that's 1, 2, 3, 4, 5, 6. And then coming off of carbon number 1 is a chloro, CHLORO. Whoa, that was weird. I think I need to get a new tip on this pen. Anyway, okay, So coming off of carbon number 1 is a chloro. But that carbon has to be carbon number 1. It can't be any other number. So when I'm naming this, I don't need the 1. I'm not actually on a test. I wouldn't mark it wrong if you put a 1, but it's like having a formula like NaCl. How many sodiums do you have? 1. How many chlorines do you have? 1. It's an understood. It's the same sort of thing. So you would just call this chloro. That's my substituent. And then you have your parent, which is 6 carbons long. That's the hex. ANE tells me all carbon-carbon single bonds. And then the cyclo tells me it's a ring. So I would say chlorocyclohexane. Similar sort of thing for this one, in that this carbon has to be carbon number 1. And it doesn't matter if I go clockwise or counterclockwise when I'm numbering. So let me number these. I'm going to go 1, 2, 3, 4, 5. There's no other substituents. If there was another substituent and it mattered, then we're going to have to worry about it. But we're not to that point yet. So here's our methyl. And it's coming off of carbon number 1, but I don't have to say that. So you just say methyl, then it's a ring. And then pent tells me there's 5 carbons. And then ANE tells me I'm all carbon-carbon single bonds. So a lot of times it's easier to start by going from the name to drawing rather than from the drawing to the name, just to get until you get comfortable. All right. So when we talk about isomers, we've only talked so far about isomers that are in a straight chain. But if you have isomers that are in a ring, other weird stuff happens. So we know that if we have a straight chain alkane, so something that's, however many carbons long, I can take, and I'll show you guys in class with models, right? These are my hydrogens. I can take this carbon in the end and I can actually rotate it around. I can go in a circle with it, right? It doesn't matter. It will have free rotation about this bond right here. Free rotation about this bond as well. But if I have something that's in a ring, right, then there's no rotation. There's no possibility of rotation. It's limited by the fact that all the carbons are interlocked, right? And it's going to be easy. I'm going to bring some models in to class, and it's going to really help to see those models. And so if you have substituents that come off of a ring, and let's say each of the substituents, there's one coming off of this one and one coming off of this one. Well, the question is, this ring is in one particular plane, and the substituents aren't going to be in the same plane. They're either going to be above the ring or they're going to be below the ring. And so you have to be able to say, even though it would get exactly the same name, you have to explain that different arrangement of atoms in space. And so when we look at these, here's kind of an example where we have 2 rings. And in this case, we've put our 2 chlorines. We have 2 substituent chlorines, and they're both going basically below the ring. So if we have the chlorines facing down and they're both going in the same direction, I could flip this molecule and these 2 would be exactly the same. Now, I'm not going to draw the hydrogens because I'd be here forever. These 2 are the same thing. Either they're both up or both down, but they're on the same side of the ring. They're either both on top of the ring or both below the ring, and we call that cis. If the chlorines or the substituents, whatever they are on opposite, now this would be the same as if I drew this, where the chlorine on this side went down and the chlorine on this side went up. These are both examples of trans configurations, TRANS. It's like a transatlantic flight. You have to cross the ocean. Well, here you have to cross the plane of the ring in order to get to the other substituent. So the rest of the name is exactly the same, 1,2-dichlorocyclohexane, which you could practice naming if you'd like. But you have to say that those two things, these two molecules, are not the same. Not the same, right? These are both trans. Both of these are trans. Both of these are cis. But the two groups here and here are not the same. So you have to give them different names. So when we talk about alkanes, we have to think about the conformations of all the atoms in the molecules. And we know that all atoms are surrounded by electrons, right? And all electrons carry a negative charge. And so really atoms want to be as far away from each other as possible. And you'll know this because you learn VSEPR theory, the valence shell electron repulsion theory. And so when we look at how atoms are arranged in alkanes, what we can see is that if you had something like, let me come down here, like this. Do you see how these hydrogens are relatively close to one another? Whereas if I come over here, that's called the ellipsed conformation of ethane. Whereas if I come over here and I lined it up, this would go between this hydrogen and this hydrogen. So they're a little bit farther apart. They're less crowded. The atoms are less crowded. And we call it the staggered conformation. So if we were to continue to add atoms, we see this staggered conformation because the atoms are trying to get as far away from each other as possible because they're surrounded by electrons that are all the same charge. So these ellipsed conformations are energetically less favorable. So they typically tend to adopt the staggered conformation so that atoms are less crowded. So you can kind of see this also in ring structures, where if you look at the position of the hydrogens, you can see that the hydrogens are a little more stable in, we call this the chair conformation. And the chair conformation is kind of hard to see why we call it a chair, but I kind of like the name of the other one. The name of the other one is called the boat conformation. And if you kind of see, it sort of almost looks like a boat, right? Where you have kind of high ends on the sides. And so that's why they call this the boat conformation. And the chair conformation kind of looks like the seat of a chair, but you know, sort of. But when we look at rings, we want less crowding, and that's what we see. This is less crowding, which is very important for stability. So the very end of this chapter are reactions of alkanes, where we have to look at what can happen to alkanes. And so we know that alkanes can be oxidized. And we do this all the time. When you're driving a car, what are you doing? You are oxidizing alkanes because that's what gasoline is. It's alkanes. And we call that combustion. If you burn alkanes in the presence of oxygen, it's combustion. And that happens not only in our cars, but also in our bodies. That's how we break down sugars. Glucose is an example of an alkane. And we break it down with combustion, which is kind of cool. You can also react alkanes with halogens, usually chlorine and bromine, and we call that halogenation. And so all you do is basically replace a hydrogen with a halogen. So it's pretty easy. So combustion, there's two different kinds of combustion. There's complete combustion, where you have your hydrocarbon, you have your oxygen, and they burn, and you produce only carbon dioxide and water, and then heat energy. But our cars do not do complete combustion. Our cars do incomplete combustion. And in incomplete combustion, we make carbon monoxide, water, and heat energy. And this is why you do not run your car in a garage and be in your garage, because carbon monoxide will build up and it actually binds to the hemoglobin in your blood more tightly than oxygen does. And so you will starve your body of oxygen if you do that. So never, ever, ever be in a garage, a closed garage with a running car. Do not do that. Okay, halogenation is it's called a substitution reaction, where we're replacing a group, and in this case, it's going to be a hydrogen, for another, which is a halogen, right? And so the product is going to be an alkyl halide or a haloalkane. Either way, it's the same thing. And we're also going to make a hydrogen halide. So like HCl, right? Something like that. All right. So this is not, halogenation is not a reaction that we typically do in our bodies, but some of the drugs that we use on patients and things like that, you do need them to be halogenated. And so we'll talk about that later. But halogenation doesn't occur by itself. You need a catalyst like heat or UV light to make it happen. So if we start out with an alkane and we're saying, okay, this alkane, maybe it's really long, but we're just saying that's the rest of the molecule, right? Maybe it goes on forever. We don't know how long it is, but that's what the R stands for, the rest of the molecule. So now, in the presence of a halogen may be Cl2, right? And in the presence of light or heat, one of those chlorine atoms, so Cl2 is like Cl bound to Cl, one of those chlorine atoms is going to go and replace a hydrogen. So the hydrogen is going to take the place of the chlorine, wherever the chlorine was. So you just basically swap them. So here, this would be the Cl, and then here's my hydrogen. This would be the other Cl. So that's what made the swap. That's why we call it a substitution, because all you're doing is swapping. Same thing, here's an example where we have methane. And we have bromine, and that's Br bound to Br. One of the bromines is going to go and replace the hydrogen there. So we have a Br bound to the methane, and so now we call it bromomethane. And then our hydrogen is now attached to the other bromine, so we call it hydrogen bromide. And so these are just other examples of exactly the same thing. And that is it. It's the end of chapter 10.